Hi, and welcome to another lesson of Introductory High School Chemistry. Today we are going to be talking about enthalpy and chemical reactions. So as always, please feel free to enter any questions or comments in the comments section below, and we'll get started. So last time we talked a bit about how gas laws worked and the idea of heat and work as both being part of energy. So today we are going to be talking about enthalpy, which is also a term that is used to describe the energy released or gained by a chemical reaction. So to start, let's have a bit of a review of what work and heat will be. So we learned last time that the equation for heat would be Q equals mc delta T. And that would be the heat. And then we learned that work would be negative P delta V. So let's write these two equations down and have a quick recap of what they mean. Oh, okay. So, apologies, this paint tool is not exactly showing up. Can you see this on your screen? Okay. Cool. Okay, well, we're just going to have to work with this. Alright, so thank you, Diane. Alright, so let's start by writing down the two equations. Alright. Thought that was going to be blue. Q equals mc delta T. And let's just make heat red. Oh, my apologies. Well then, let's make work red. Work equals negative P delta V. Now, what does m mean here? That's mass, the mass of the object you're measuring. C is the specific heat of the object, or the ability for the amount of heat that the object can absorb before transferring it. And delta T is the difference in or the temperature change. Whenever there's a delta in front of something, it means there's a change. So work is pressure and the change in volume. It's related to gas laws, as we sort of mentioned last class, and so remember at the end of class when we were talking about the conversion between work having the units of joules and pressure and volume having the units of ATM times liters. Well, it turns out that there is a conversion factor. When you multiply the gas constant of 8.31 joules per mole K and divide by the gas constant 0.0821, which are the two R's that I mentioned last time. And by doing this, you cancel out the units of temperature in moles. So you will notice then that 1 liter times ATM is equal to 101.325 joules. So let's just write that down here. Okay, so this is in ATML, and this wants to be in joules. So you would have to multiply this by 104. Okay. Whenever you're doing unit conversion, the thing that you have already, the units that you have already have to go on bottom, and the new units are on top. So 1 ATML is equal to 101.325 joules. And you can convert that to kilojoules and such, and if you need work in kilojoules. So I'm just going to write that conversion over there. Now let's look at enthalpy. Okay, so enthalpy is sort of a fancy way of quantifying the change in energy when a reaction happens. So every chemical reaction involves the breaking and forming of bonds in between molecules. So in between atoms. So here we define the enthalpy change as the heat of a process when pressure is held constant. So delta H is equal to Q at constant pressure. This makes sense with what we already know. Yes. So H stands for enthalpy and delta stands for change. So change in enthalpy of a reaction is the change of heat, sort of, between the reactant and going to the products. Alright, so, okay, I guess we will take a look at this example that they put. So this equation is described as a thermochemical equation. And here they are writing one for PCl3 in gaseous form, Cl2, and PCl5. And there's an enthalpy change of negative 88 kilojoules. So this thermochemical equation is balanced, and it has a delta H of negative 88 kilojoules. This may seem repetitive at first, but it really makes everything very clear in terms of which way the energy change is going. So we read just above that there are, or actually we haven't read yet, sorry. Well, delta H can be positive or negative. So if this is negative 88 kilojoules and you wanted to, actually this may be easier to sort of explain when we've taken a look at how the bonds are working in this scenario. So let's go back to the canvas and take a look. Alright. Let's just move to another corner of this small piece of paper. Okay. So let's take a look at how bonds work. So when you're making bonds, when you're forming bonds, you have two things that are attracted to each other, and they are given the opportunity to fall together to form a chemical bond. And since we know that bonds tend to form because they make both atoms more stable, they lose a lot of the potential energy that they stored when they become more stable, because that means that they are both at a lower potential energy state than they previously were. So this means that forming a bond releases energy. Okay. So energy is released. Ooh. Okay. That is not what I want. That is not what I want either. Oh my goodness. Okay, well, we're just going to pick a brighter yellow. Energy is released, so it's going out. Okay, and when we're breaking bonds, energy is being used to break the bonds, because imagine trying to pull two magnets apart. That requires some force, right? Because there are two things that are attracted to each other, and therefore energy is required to make this process happen. An outside force is required to break the force of attraction that is between these two molecules, or sorry, these two atoms. So, which of these processes, so both of these processes involve a change in delta H, or a change in H, or delta H. So, which process do you think would have a positive delta H and which would have a negative one? Of course, in actual chemical reactions, it is not this simple. Okay, so forming bonds. Okay, rewind. So delta H is related to the energy of a system, like work is as well. So when we talked about work, expanding gas means that the system, or the gas itself, is losing energy. And therefore, when a gas expands, the work is negative, and when a gas contracts, it's the opposite. So the gas is the work is positive. So here it's the same. Enthalpy is talking about the energy, the change in energy of the system, when in this case would be the two molecules that are forming or breaking their bond. So let's think about it from the point of view of the system then. So when you're forming bonds, the system is losing potential energy because they are falling to lower potential energy states. When they're in their bonded state, it has lower potential energy. So therefore, energy is being released. And when you hear the phrase energy is being released, that means it's an exothermic reaction. We haven't really gotten to this point in the explanation yet, but basically, it means that the delta H here is negative. Because the system is losing energy. The energy is escaping. And here, conversely, delta H is positive. And energy has to come into the system in order to break the attractive bonds between these two atoms. So the system gains energy, and that's how the bonds are broken. Okay, so the textbook kind of explains. Actually, it doesn't really explain, but names these types of reactions. So, if delta H is negative, of course there's always, okay, of course there are usually going to be more than one, two molecules or two atoms reacting with each other. But in order to simplify it, we're just going to say forming and breaking like one bond. But in reality, it's much more complicated. So we call reactions that have a net delta H of that is negative exothermic. Okay. So therm is sort of like a root, or you've heard therm in thermal, which you usually associate with heat, and exo is sort of like going out. Here we call a positive we call a reaction that has a positive delta H endothermic. So it requires energy, and yeah, the system requires energy. So those are the two terms that we will keep bringing up while we are talking about enthalpy. Alright, so let's go back. Okay, so yes, it's gaining energy if delta H of a process is positive. And if delta H is negative, it loses energy. Yep, we got it. So the textbook presents a pretty simplified graph of how this would look. So we have energy on our y-axis and reaction progress on our x-axis. So when you go from reactant to product, if you add energy, the products will have a higher energy level than the reactants. In the opposite case, if the reactants start with a higher energy level and there's energy leaving the system, you get a lower energy state of products. This means bonds are being formed, and A means that bonds are being broken. Yes, that is a little counterintuitive, but it'll make sense. Please let me know if it doesn't. Okay, so they present a pretty simple graph over here, but I kind of want to make it more complicated, because that might tell us a bit more about the process. Okay, so here's an axis, and we call this potential energy, because that's technically what we're referring to when we say energy. And here is the energy level of the reactants, and here's the energy level of the products. Let's just do that in different colors, because it's fun. So that's the products, and that's the that's the red is the reactants, and the blue are the products. And there's going to be a little journey taken. I wonder if you have seen this kind of graph before. And this is going to be time or reaction progress. Actually, it is not going to be time. It's going to be reaction progress only. So, as you can see here, the energy level of the reactants is higher than the energy level of the products. So there's going to be a change in energy here. And what is it going to be? Well, we are always doing final minus initial subtraction in chemistry. So the way you would figure it out, even though this graph isn't very detailed, is you would subtract the final energy level of the system from the you would subtract from the final energy level of the system the initial energy of the system. And since the initial energy of the system is higher than the final, you get a negative number for that, and that is your negative delta H. Now, you can sort of see it from the way this graph looks that it could be this space here. That is the difference in energy, right? Because that's what we just did. We subtracted the difference. Well, it's actually a little more complicated than that because although you could call this part delta H, there are a couple other factors that sort of influence the rate of this reaction, or not rate of this reaction, sorry, but how this reaction works. And one of them is called entropy. We will get to that probably next lesson. So let's just continue with this enthalpy idea for now. Alright, so that is sort of a reaction graph drawing, I guess. And it goes the same if you try to draw it's like vice versa if you try to draw an endothermic graph. So, same thing, potential energy. Now the reason we call it potential energy is because we think of it as molecules falling together, which is forming bonds, and I guess falling out, I don't know. So when something is falling, its potential energy is decreased because potential energy is what? Energy that depends on a molecule's position. So if the atoms that can be bonded are not bonded together, they have potential to be bonded together if they're close enough. So I guess that's what the potential energy sort of means here. So yeah, let's continue with the graph. So this time the products are up here and the reactants are down there. Wow, it's really looking like an uphill battle. Oh. Stop picking the color. Okay, it's really looking like an uphill battle for the reactants. Oh my goodness. Okay, well, that's just gonna be the color. Ah. Okay, well, oh my goodness. I forgot how I did this before. Okay, well, they're just gonna have to deal with it. Okay, so now this is sort of just gonna go up. Well, usually it does not go smoothly like that because there's this thing called activation energy. I guess we should probably touch on that a little bit since I'm already drawing graphs this way. Oh my goodness. Well, we're gonna have to draw this line again. Okay, sorry for taking up so much time trying to draw things. Okay, so let's just do it like that. In this case, the reactants have lower potential energy than the products, which likely means that there are more bonded reactant particles than there are bonded product particles, or the number of bonds is more in the reactant particles, etc. But the point being that this reaction needs energy to function, or to essentially go. So when we did, so this is also reaction progress, but I'm not going to write that there. Above, we sort of described there to be a change in the energy level. This is not exactly delta H, but you can think of it as the direction it's going. And in this case, delta H would be positive. Alright. So activation energy is this little part right here. And no matter, well, in this case, it's actually this entire thing, because that's the hill it has to get over to perform the reaction. And above here, it's this part. So that is sort of referred to as a minimum energy necessary to start a reaction. And we will get back to that in a later lesson. Oh my goodness, you couldn't see any of that, could you? Okay, well, here, let me show you what I've done. Alright, sorry about that, I didn't even notice. I will be better about that in the future. Okay, so here's the potential energy graph for an exothermic reaction. So here are the reactants, products, activation energy, usually denoted this way, and something that will tell you the direction of delta H, whether it is positive or negative, but is not exactly representative of delta H. And here we have the endothermic graph. As you can see, the activation energy is much larger because it requires energy. And potential energy again, this is the energy of the reactants, and this is the energy of the products, and it has a positive delta H. Okay, so apologies for that. I hope you guys still saw most of it. If you didn't, please let me know. Sorry about that. Okay. So first of all, or I guess the last thing we're probably going to do today, is look at this thermochemical reaction on the textbook. So 2CO2 plus O2 goes to 2CO2, and the delta H is negative 565 kilojoules. So what kind of reaction is this, and is the energy given off or absorbed? Well, so take a look at the delta H value, and that is where you'll see. So we said that negative delta H values are exothermic because it releases energy. Energy is going out. And how much energy is given off or absorbed? Well, the energy is given off, and it's 565 kilojoules of energy that is given off. Okay, so we will get more into this next time. I'm sorry for how the lesson went today. Thank you very much for watching, and please leave any comments and suggestions below. Thank you very much. Have a good day. Bye.